Myself, Srinivasan, working as a faculty in the Department of Mechanical Engineering at Shishinova College of Engineering Technology. In the last lectures, we discussed about autoencoder, and autoencoder has some certain limitations which cannot generate a new image. So, in order to have that, and we move on towards variational autoencoder. So autoencoder, as is discussed in the last lectures, autoencoder has certain limitations. It doesn't guarantee any meaningful features. For example, if you have an image of 3 and it can produce Lacan space vectors of different, and if it is a thin or if it is thick and different lattice space vectors can be produced. Okay. So it is very, even if it is a 3, the the image, it has the letter 3, it has different vectors. So it doesn't guarantee any meaningful features. And even though it compresses and it creates a new image and it creates an image from the input, it doesn't go for any classification and prediction and any job that does for that ML job does. So the recorder part cannot generate any new samples because of the unstructured space. It doesn't give any structured one, but each whatever the input that we have, it is mapped to the certain points in the lattice space. So it doesn't give the whatever that output that it produces, it is will be a garbage. So that is a disadvantage of this, and as we encounter in ML and EM, we will have some bore fitting issues, and the reconstruction loss might be reconstruction loss might be huge. It depends on the latent space that we have. So these are the limitations that we have in autoencoders. So not to have that, not to overcome this, and we go towards variational autoencoders. Okay. So in the variational autoencoder, what we are doing here is that we are trying to have this probability distribution. Suppose we have this input image and we have a decoded part and we have a Latin representations. So whatever that lattice representation, that is going to be a probability distribution of it. And we not avoid this overfitting issues. We add some regularization techniques. So this is our sample image. I mean, this is a sample one, and we have that data set we have many data points. Okay, so each data point will belong to certain classes. Okay, suppose it depends on the similarity. It goes to certain data points will go into this C1. Okay, certain data points will go into C. So this is basically a condition probability. So even though that distribution is not structured one, we don't know whether it follows a Gaussian distribution of the normalized or points and whatever it is. So we don't know those categories. And not to have that, the idea of a generative model is to create new sample. So suppose if you have a data, then that data will go into the decoder, input part, and it will generate some latent space. From the latent space, we try to get some more samples. It is not the whatever that we fed into the systems. It is basically a new images, new samples, new data, I can say. Okay. So that can be that is going to be the then whatever that is generated is going to resemble like a data. So it is a basic idea of generative model is basically it is going to be the new X. Okay. So what are the new X has been generated? It is going to be the probability distribution of the new X is going to be approximately same as the whatever that we have given in the input. Okay. So that's why it is called generative model. So the advantage that in the autoencoder basically produces this unstructured data, and whereas variable autoencoder produces the probability structure on the latent space using the 3R distribution, because since we use this probabilistic latent space, and we go by Bayes rules. Okay. So this is basically a Bayes rules, and we encounter two kind of distribution in variable autoencoder. One is basically a encoded part. This is an encoded part. This is a decoded part. And whatever the data that we have, that is our input, and whatever latent space, the probability of this is that the latent space is basically, it is mapped with the help of this posterior distributions. Okay. So basically, in the autoencoder, and it is going to be random, and here it is going to be a distribution. So that distribution is going to follow this Gaussian. And the basic, this is basically a posterior one, non-probability. This is a likelihood. This is a prior one. It is going to be a non-general one. Okay. So basically, we are interested in indicator part, and in indicator part we are interested in. This first one is basically prior distributions. So how do you find this prior distribution? Basically, you have to, if you want to find this probability of x, and we have to use this probability of x given probability of z given x. So when you want to compute this marginal one, and it is very hard. Okay, basically we are going to find out where we're going to get the probability of x over all latent space variables. Okay. So finding out is very difficult because of the high dimension. So what we can do here is that we can go for the new approximations, the new distributions. So instead of p of x given x, we can go for another distribution q as a q x given x. So that if you use this new distribution that follows this Gaussian one. So the Gaussian one, it is going to be 0 mean, and the variance is going to be 1. So variance is going to be 1. So basically we are trying to get, we used to approximate by using this new distribution. So here also this probability of x is also follow this Gaussian one. It is going to be the reference distribution. So that makes, because of this probabilistic in nature, it makes makes a structure well, and it is continuous in latent space. Whereas in autoencoder, and it is not a continuous one, there is a disconnect will be there. So in order to find this K, one can know this how much is deviated from the original one. Whatever we have got, it is going to be f x. It is going to be, when you use this Bayes rule, and it is going to be slightly different from what is there in the p of x. So that KL divergence is basically to find out the difference between q z even x and p z even x. So because we have used the new distribution, we have the new approximation, it is very close to that, but it is not exactly same. So that is the advantage of using variable autoencoder in encoded part. So next class we'll discuss about decoder.